Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, the sea. The sea exhibits a number of phenomena that are physics related, including the tides, tidal resonances that occur at certain locations on Earth, and finally the waves that travel along the surface of the sea. So let's look at the physics of those various phenomena. And I'll start with the tides. The tides are caused primarily by the moon's gravity, and to a lesser extent, the sun's gravity. So let's set the sun aside for the moment and just consider the moon and the earth. They're actually orbiting one another, which means that they're falling freely towards each other. And of course, they don't hit each other because they're moving sideways fast enough that instead of like just crashing together as they accelerate and hit, they're moving sideways and they end up orbiting their combined center of mass. So you could think of the moon as orbiting the Earth. That's pretty close to true, but to be more correct, both objects are orbiting, but it's the center of mass of the pair that they're orbiting. That means the Earth is doing a little bit of a dance as well. Okay, but the big issue is that they're falling towards each other in the sense that they're accelerating towards each other, and the strength of gravities now begins to matter. We won't worry about the strength of the Earth's gravity on the moon. Let's consider the strength of the moon's gravity on the Earth. The moon's gravity on the Earth varies with location on Earth. The parts of the Earth that are closest to the moon experience the strongest moon gravity and would like to fall faster than the parts of the moon that are farther from the parts of the Earth that are farther from the moon and experience weaker moon gravity. So, the part of the Earth closest to the moon would like to fall faster, accelerate faster, but it's attached to the rest of the Earth, and so it can't. That parts of the Earth that are closest to the moon, if I didn't say it correctly, they tend to fall faster than the rest of the Earth, but they can't quite pull it off. How about the parts of the Earth that are farthest from the moon? They would tend to fall slowest and get left behind as the rest of the Earth accelerates ahead of them. But of course, because they're all attached, they can't separate. The result, however, of all of this, the falling and the tendency to fall unevenly because of the varying strength of the moon's gravity on the Earth, that uneven falling causes two bulges in the Earth's oceans. Because the oceans are liquid, they can move about a bit and shift their distribution. And what happens is a bulge appears on the Earth's oceans on the side of the Earth closest to the moon. And a second bulge appears on the Earth's oceans on the side farthest from the moon. Those two parts of the Earth, the closest part of the Earth you can think of is trying to fall faster and get ahead of the Earth. And the far side of the Earth, one farthest from the moon, tries to fall slowest and gets behind the Earth. It lags behind. So bulges appear on both sides of the Earth, nearest and farthest. If the Earth weren't turning, those bulges would just sit there and everything would be great. But because the Earth is rotating, the location of those bulges has to evolve with time because the Earth turns and different parts of the Earth become closest and farthest from the moon. Similarly, I should also say that the moon is moving as well. So all of this complicates things. But at any given moment, there are two bulges on the Earth's oceans. So as the Earth rotates, where those bulges are located moves. The bulges actually tend to lag a little behind where they would be if the Earth weren't turning because it takes time for the water to move to create those bulges. But basic idea is there are bulges on the near side and far side of the Earth. And as those bulges shift their location on the physical geometry of the Earth, we sort of watch them go by. So if you're standing at the ocean side, and the bulge is beginning to appear near where you're located, you watch the water level overall rise up because you're now entering one of these bulges, or rather, one of these bulges is developing around you. And as the Earth turns and your location here at the seaside works its way towards the neither bulge. It goes from it wasn't where one of the bulges is, it goes to where the bulge isn't, the sea level drops where you are. And then as you get to the other bulge, the sea level rises. So a person standing at the seaside, near the equator of the Earth, approximately, where the bulges are strongest, because the Earth is spinning about an axis that's similar to the plane of the Moon Earth orbit. As the Earth is rotating, and you're near the equator, you watch the bulge appear, you watch the bulge disappear as you move out of that bulge area, then you move to the other bulge, and then you watch it disappear. So approximately 4 times a day, you go through a half cycle, I should say. The bulge appears twice a day, once when you're nearest the moon, and once when you're farthest from the moon. And those are both correspond to what is known as high tides. And when you're turned at 90 degrees from the bulges, you're at a low tide. That's when the sea level is lowest. So this approximately describes the Earth's tides. They're strongest near the equator, where the bulges are sort of centered, approximately centered. And there are 2 high tides and 2 low tides per day, approximately, because that's how often you there on the equator go from the near bulge to the middle, to the far bulge to the middle, and back. You do it during one daily cycle, approximately. You go through two bulges and 2 non-bulges, 2 high tides, 2 low tides. It's approximately per day because the Earth-Moon system are moving, and so it's not exactly a 24-hour cycle. It's more complicated than that. Okay, so superimposed on this cycle of moon tides, the bulges and the bulge, from the bulge to the non-bulge to the bulge to the non-bulge and so on. There's also the effect of the sun. The sun also creates its own bulges on the Earth. They are not synchronized with the bulges due to the moon, and they're not as strong. They're about 1/3 as strong as those from the moon. And that's because the sun is so far away that the sun is very far away, but its gravity overall is much stronger. It's much more massive. So when everything settles out, you get minor bulges caused by the differences in gravity for the side of the difference in the sun's gravity for the side of the Earth closest to the sun as opposed to the side of the Earth farthest from the sun. So you've got another pair of bulges imposed by the sun's gravity and the non-uniformity of it across the Earth. And those bulges by themselves would create minor tides, but they have to work together with the tides caused by the moon. And there are times when the sun's minor tides coincide with the moon's major tides, stronger tides, and both the bulges coincide, and they make particularly strong bulges, and you get particularly dramatic tides. The high tide is especially high, the low tide is especially low. And I think those are called spring tides. And there are also times when the sun's bulges are at right angles, 90 degrees shifted relative to the moon's tides, and that kind of cancels out the effect to some extent. And you get wimpy tides, and I believe they're called Neap Tides. So tides are primarily caused by the moon's gravity and the fact that it's not uniform across the Earth. And they're influenced by the sun's gravity, introducing a cycle of especially strong moon tides and especially weak moon tides, or really total tides, I should say. The total tides are periodically very strong and periodically rather weak. They cycle with approximately the cycle of the lunar month. As the moon goes around the Earth, that influences when the strong tides and the weak tides are present. Okay, so that's the story of tides on Earth. How about tidal resonances? Well, I mentioned a moment ago, a little while ago, that if the Earth were rotating, the bulges on the Earth's oceans would be very simple. And this is without leaving the sun back out of the story. If it were just the moon, and the Earth were just sitting there always facing the same side of the Earth towards the moon, You would have a bulge near the moon, and you'd have a bulge far from the moon, and they would just sit there and they would be no problem. But because the Earth is moving, the bulges move relative to the Earth's surface. And for that to happen, the water has to move. It has to actually flow. You can't just build a bulge at your particular seaside without having water come in from somewhere else. And that takes some time. And it affects when the bulge reaches its peak height at your location. So there's a little bit of, there's some complications in the motion of the water on the Earth's surface as driven by the tides. And in certain locations on Earth, special locations, the movement of the water, trying to create the bulges and trying to create the anti-bulges, the non-bulges, causes a sloshing motion. And the sloshing motion, if it's timed correctly, can lead to huge sloshes of water. And the classic example is the Bay of Fundy in Nova Scotia, where the water in that basin, or that volume of water, begins to slosh. And it is sloshing dramatically, and the tides, the rise and fall, the level of the sea there are dramatic, tens of meters. And where does this come from? Well, that certain bodies of water are essentially extended systems with approximately a limited size. And they can develop standing waves as their modes of vibration. In fact, those modes behave as harmonic oscillators, and you get these sloshing motions, which are, you can think of them as a musical instrument that plays a very low-pitched note, and you get it going rhythmically, and it really gets a huge amplitude of that harmonic motion, harmonic oscillation. And a simple example of something that does this is just a basin of water, a sink or a bathtub. If you just let the water sit still, it has an equilibrium arrangement, which is level surface. Nothing, no high points, no low points. But you can slosh the water in that limited system, that basin, and get various complicated motions. You do this, you get all kinds of complicated motions. But in principle, you can assemble that overall motion out of special modes that are themselves harmonic oscillator behavior. So the fundamental mode of water sloshing in essentially an aquarium or a bathtub is one in which, as you get it going, one end the water level rises, the other end the water level falls, and it goes rhythmically back and forth like that. And it's a standing wave. It's got one node in the middle and an antinode at both ends of of displacement from center. So there's a node of displacement from level. The node means it's not moving up or down. The two ends go up and down like this. And the curve of that water is going to be a sinusoidal curve. It's going to have trig functions show up magically in these complicated systems. But there they are. So that's the fundamental mode of vibration for water in a basin. I should say that this is a gravity-driven system. The restoring force that shows up when you go off-center involves gravity. So a lot of what happens on the surface of water involves gravity. They're gravity waves, often they're described as. This is a gravity standing wave. So it's a standing wave which is typical of a system that has finite extent. It has an end on both sides. It doesn't go on forever. And the standing wave is driven by gravity, and it's a dancing in place motion. And in the period of this motion depends on how strong gravity is. The stronger it is, the faster the motion will go. And it also depends on the length of the basin. So if it's short, like a sink, it's going to be doing this. If it's longer, like a bathtub, it's more like this. And if it's as long as several miles long, the rhythm of that sloshing motion, it could be 12 hours, the period, 12 hours, and timed to match the tides. And if it's timed to match the tides can get the sloshing motion going rhythmically by resonant energy transfer. The tides cause the water level outside the sort of basin area to rise and fall, which gives little shoves to this sloshing motion, and the sloshing motion gets bigger and bigger and bigger, it's limited by losses. Energy is coming into the sloshing motion from outside, driven by the tides. The sloshing gets bigger and bigger until finally it's losing energy by viscous forces and other things as fast as new energy is coming in. So the sloshing motion builds up, and ultimately it builds up to a maximum and doesn't keep building forever. It eventually reaches a sort of static level. But that is a tidal resonance, and there are tidal resonances in various places around the Earth. The most extreme that I know of is the Bay of Fundy, which has a dramatic resonance driven almost perfectly. It's almost perfectly timed in its period to match the tides, and so the tides drive this sloshing motion. And you get these dramatic rises and falls in the water near the end, where you're at the antinode of the rise and fall. Okay, so that's the story of tides, the story of tidal resonances, which are standing waves on a finite system of water. How about if you break out into the open sea and look at things on the open surface of the water? And the open surface of the water also has an equilibrium, which is flat, modified slightly by the tides and the bulges, okay? But set that aside. Flat is the equilibrium, but you can disturb it away from equilibrium, and then things begin to move. And because it's a system with an extent that goes on essentially forever, the modes of motion or vibration in this surface are traveling waves. They go on, they're waves that move. Sound waves move. In open air, the modes of vibration of open air in endless extent are traveling waves, so off they go. And on the open surface of the water, which is also essentially open forever, an extended system that goes on forever, the basic modes of vibration are traveling waves as well. Again, they involve gravity. If gravity vanished, well, the water would be in trouble in general. But if there were no gravity, there would be no energy to be released by having a high point and a low point. You can't release energy from going from high to low if there's no gravity. So there's no gravitational potential energy left. So gravity is involved in these waves. And they're called gravity surface waves because they're motions at the surface of the water. The ripples and things that you see, and the breakers that you see whizzing across the sea, they involve gravity, they involve the surface of the water. They don't go down forever into the water toward the bottom unless the bottom is very shallow. There are motions in the top surface of the water. In fact, if you watch one of these waves, and the waves I have in mind are not the little waves of you tap the water and you make the little waves, those actually involve the surface tension of the water. They're not entirely driven by gravity as the restoring force. They also involve the fact that water itself has a tension on its surface. When the water ends and air begins, the water tries to minimize that exposed surface. The molecules pull toward each other chemically, and they create a tension in that water. And disturbing the water on very small scales bends that, the tension fights it, and it pulls back. So the little teeny waves, set them aside, another story. The bigger waves, these things and these things, those are gravity driven. The restoring force is all about gravity. And they have various characteristics. For one, they have a wavelength. So the simplest modes of traveling waves have a rhythm to them in space. They have a crest, a trough, a crest, a trough. The distance between two crests, or equivalently two troughs, is known as the wavelength. It's a distance from crest to crest or trough to trough. And you can have wavelengths that are small, maybe a meter. If you get too much smaller, you're going to get the capillary waves, which are surface tension. Set them aside. So the decent sized waves, they have a wavelength, a meter, they can be 10 meters, they can be 100 meters, all those things. And they have a wave velocity, which is how fast one of those crests moves along through the water. And that's more straightforward. It turns out that the waves on water like this travel they don't have a single speed at which they travel. Sound waves in air have a single speed at which they travel. Depends on the density of the air and primarily on the density of the air. the water waves, they're more complicated. They travel at a speed that depends on their wavelength. The longer the wavelength, as the farther apart the crests are on a given wave, the faster it travels. So the short waves like this, they go slow. The big long waves, they go fast. The very long waves, they go quite fast. The relationship's complicated. It gives the wave speed. But the longest wavelength of the waves, so that we ever experience on Earth, are the tsunamis, previously known as tidal waves, which have nothing to do with the tide, so they were renamed. So tsunamis, they have very long wavelengths, and they therefore travel very fast. So that's an observation to go with. Another observation about waves is the depth to which they affect the water depends on their wavelength as well. So basically the water is only affected approximately in proportion to the wavelength. So if you're watching a wave go by and it's got a wavelength like this, it's a meter, the water is doing something up here, is disturbed. But if you go about a meter below, or 2 meters, or 4 meters down, you go some wavelengths deep in the water, you don't notice the waves anymore. The motion of the water several wavelengths below the surface is negligible. So the wavelengths are all about motion within about a wavelength of the surface. That means that the little waves like this don't affect fish swimming down 2 or 3 wavelengths deep in the water. They don't even notice. The big waves that have long, by big I should say big wavelength, not necessarily big amplitude, big wavelength, those dig deeper in the water. They affect water deeper down. Because the wavelength's longer, they reach deeper into the water as well. So that's an observation. The waves traveling along the open sea, where it's deep, all the waves are basically affecting, they all reach about a wavelength into the water, and even the long wavelength ones, when they reach a wavelength into the water, they're still dealing with water. But as it gets shallower, as the sea gets shallower, now there's some issues. The short wavelength waves may still be able to move along properly without touching the bottom. But the long wavelength waves begin to notice that there's a bottom to the sea as the sea gets shallower. It gets down towards 1 wavelength deep or less. All right, so the waves travel along. They travel with a speed that depends on their wavelength, and they dig at various depths into the water, depending on their wavelength. What actually is going on in the water itself? Is the water moving with the wave? And the answer is no. As the wave goes by, this undulation, that pattern that moves, the pattern moves, the wave structure moves, but the wave structure is built out of local water, meaning that the water doesn't travel with the wave. It moves about, but it stays approximately in place on average. And actually it moves in a circle as the wave goes by. The water truly travels in a circle. And you can see this if you look at debris floating on the surface of the water. A note in a bottle. Put the cork in, put it in there, watch it bob up and down. That, as the wave goes by, the bottle will travel in a circle. It's giving you a sense of what the local water is doing. And the local water is undergoing a circular motion. Its top surface, the top of the circle moves with the wave, the bottom moves against the wave. So as the wave is heading off to your right, that is the structure is moving to the right, the bottle will be doing loops like this, with the top going to the right, bottom going to the left, top, bottom, right, left, right, left. All right, the circles continue deeper into the water, but they fade away to almost nothing by the time you get about 1 wavelength below the surface. So that's the structure of one of these waves, and it travels along. The amplitude of the wave doesn't have a strong influence on how fast the wave moves. If it's got a wavelength, it moves at a certain speed. So you can make a wave that's got a certain wavelength, that's got a gentle rise and fall. That's a low amplitude wave. If you've got a big rise and fall in the wave, that is a large amplitude wave. Well, so what happens when one of these waves gradually approaches the shore and the water gets shallower? Well, once the water gets shallow, so that there's no longer one wavelength of water available. It's getting less and less and less. The wave starts to have trouble. It can't move in full circles anymore. To create the proper wave, the circles get squished. And with this, a couple things that are interesting happen. First off, the wave slows down. So for that given wave, instead of moving forward, suppose it was moving forward at 10 meters per second, it's now down to 9 or 8 or 7 meters per second. What that causes then is the wave crests begin to pile up. As the ones that are close to shore have slowed down, the ones that are far from shore haven't, they pack tighter together. So the wave crests bunch, and that makes the wave look to someone on the shore like it's more dramatic. The edges are steeper because the crests and troughs are squeezed closer and closer together. So the wave looks more threatening because of this steepening effect that accompanies the bunching of the crests. So that's one observation about the waves. The second is that the wave begins to have trouble assembling itself as it circles, and it eventually falls apart. It can't continue all the way onto the beach, so it runs into trouble. And one of two things can happen to it. It can either get ground up into a sort of boiling froth. It's not literally boiling, it's just frothing, a messy, turbulent mess. And that happens if the shallowing process is gradual. That is, the water gradually gets shallower and shallower until finally there's not enough water left at all. You get this grinding end to the wave. If the water gets shallow very suddenly, quickly, the wave breaks. It loses. It's almost suddenly runs out of water with which to build the wave crest. It's ultimately it's pulling water in from around the crest to build the crest. And if it runs out of water ahead of it, that is towards on the shore side of a rapidly shallowing part of the sea, it can't build that side of the crest, and the crest ends up sort of half-baked, and it ends up as the water circling creates this breaking crest that is hollow, and the water then crashes over the front end. So that's the familiar breaking wave that you see in rapidly shallowing water, and surfers ride these things. Those breaking crests and end up in sort of the tube that can be created by the crest as it breaks. So that's what happens to waves when they get too close to the shore. How about during that approach, as the wave is approaching the shore, and we won't let the wave break yet. We'll stay out far enough from the shore so the wave doesn't crumble into froth or a diving crest. We're out far enough, but it's slowing down. When the wave slows down, it undergoes two effects that occur with any wave that undergoes a change in speed. And those two effects are reflection and refraction. These occur in sound waves, they occur in light waves. So in the case of water gravity surface waves on the sea, as the waves slow down, as the sea gets shallower, you get reflection and refraction. Reflection means that part of the wave this doesn't quite reverse, of course. It bounces off the transition, like light off a mirror. It hits the transition and bounces. If the transition is abrupt, the bounce is very dramatic. If the transition is the change in speed is gradual, the reflection's less dramatic. But you get reflections. And the reflections with light are often mirror-like reflections. Light comes in, bing, it bounces off. It's only a partial reflection. You don't get all of the wave reflected, but you get a bit of it. So as the waves on the sea come in towards shore, there's a little tendency for them to send part of their wave energy back out as a reflection. There's also an effect called refraction, whereas the wave traveling along hits this transition in speed this change in speed, if it hits at an angle, its path of travel bends in the new location, in the new region where the speed of the wave is slower or faster. It bends its path. So the wave might have been coming along towards shore at this angle, and as it enters the shallower region and slows down, the wave crests, the ridge of wave crest bends. And as a wave slows down in going through one of these transitions, it bends towards perpendicular to the edge of this transition. In this case, it bends toward the beach. So a wave that was this pattern of ripples that was heading along the open sea and that comes near the beach, and that system slows down, it bends toward the beach. And this explains why waves at the seashore generally seem to be coming at the seashore. Even when they were traveling at a cockeyed angle out on the open sea, as they approach the shore, this refracting effect that occurs as the wave slows down bends that rippling structure so that it comes at the seashore more. Not completely at the seashore, but dramatically more towards the seashore. So the waves tend to come toward shore and not hit at a cockeyed angle. That refraction does the trick. So the reflection and diffraction, I should just say, are just generally, they show up in waves everywhere. They are responsible for echoes, for example. So when I clap my hands, we're hearing additional sounds because the sound wave that tries to get into the walls of this room fails. It partly fails. It's partly reflected as it tries to enter the walls. Because the speed of sound in the walls is different from the speed of sound in air, there's a partial reflection, and the wave partially comes back at us. In the walls, there's also refraction, but we're not there in those walls, so we don't pay any attention to it. So you get that effect. You get the same effect with the light when it tries to enter a glass window. The light partially reflects off the glass as light slows down in glass, and the light bends as it travels in the glass. That's a refraction effect, and it's used in lenses and so on. So you're observing me through the lens of a camera, which is making full use of the refraction effects that occur when light travels from open air into glass or plastic. Okay, so that's the story of the water gravity surface waves influenced by trying to approach the shore and slowing down. Last thing to talk about is interference effects in waves. Again, a general wave phenomenon. If you have two waves with essentially the same wavelength and therefore the same travel velocity, wave velocity, two waves that are just well matched with each other. That's what I've defined at this point. They're well matched from each other, but they're traveling at different angles towards the shore. Let's let it be on toward the shore. These two waves are traveling along, and as they begin to overlap, the location of the water's surface at any given moment is complicated. It was bad enough watching a single pattern of ripples come along and having a crest to trough, a crest to trough, a crest. But now you've got another crest to trough, crest to trough. And what does that surface look like? Well, there will be moments when the two crests coincide, and you'll get a dramatic crest, a real high rise in the water. And there will be moments when two troughs coincide, you get an especially deep plunge at the surface of the water. And those locations where the water is rising and falling dramatically because of these two overlapping waves, that's known as constructive interference. The two waves are working together to cause an especially large amplitude of motion locally. So that's constructive interference. The other possibility is the two waves overlapping and having it so that the crest of one wave, one of these pieces, it coincides with a trough of the other. So they kind of cancel each other out. And the water barely moves up and down at that location. And that's known as destructive interference. And it involves very small motions, relatively small motions of the water surface. So the amplitude is very small there. And these sorts of effects can happen in the real world with waves traveling in towards shore. They're created somewhat independently out there on the sea, And you can have waves coming from one place that are approximately matched in character to waves coming from another place. They both approach the shore. They tend to be overlapped by the refraction effect more and more. And they come towards shore, and there will be a weird effect in the arriving surf as the water comes in and grinds up or crashes on the shore. Things can get up. There can be some odd rhythms that are there. When the two original waves overlap such that they are experiencing constructive interference, their troughs coincide, their crests coincide, you get especially big movements of the water, and you get loud, heavy surf and grinding surf or crashing surf, whatever. It's strong. But then there are maybe other times when the two arriving waves overlap such that they get destructive interference. They kill each other off, and you get very little surf. And this is a phenomenon known as surf beat. So if you just sit there at the seaside watching the surf come in, there may be times when the surf is very strong, and maybe a minute later the surf will be very weak. And then it'll be very strong, and then it'll be very weak. What's happening is waves coming from separate locations working their way towards you, similar waves, otherwise similar, coming at different angles. Sometimes they're overlapping constructively, the troughs and crests coincide, big surf. And sometimes they overlap destructively, crests and troughs mismatched, killing each other off, and get gentle surf. So there's a rhythm often to the surf. It's not just bang, crash, 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 crash. It can be crash, 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 a rhythm. All right, that's enough. I think I've done justice to the sea and end of the story.